So hi everyone, my name is Kamil Bożem and I will tell you about the greatest mystery of REST API design. The mystery can be expressed with the title of my presentation: one or many HTTP requests. First, I will tell you a short story about negotiating REST API contract. Second, I will compare different HTTP versions. Third, I will show you some insights on response payload sizes. At the end, I will give you some tips. I prefer to keep my presentation in dark colors, that's why I'm turning on the dark mode now. And I hope you appreciate it. Now, I will tell you a short story about REST API contract negotiation. Imagine there is a native mobile app that allows to search for a place to stay during your summer vacation. Imagine that users can view the hotel, but there is no way for the user to read the reviews posted by other app users. This app works like that. When some hotel is selected, the app presents a new screen with loading indicator. The app requests for hotel details from the hotel service, and the app received a rich description of the selected hotel. And this is a current state. And now a product owner would like to see hotel reviews on the hotel details screen, on the very same screen. It turns out there is already a service that provides hotel reviews. Backend team wants to make the endpoint public to be used by the mobile developers. Mobile developers object. They don't want to use any additional endpoint. But backend developers don't want to make any requests for reviews from the hotel service as well. So we have a deadlock. And a lot of you probably have an idea how to solve this problem. Personally, I think there is no ideal solution. Every choice we make has some trade-offs. But actually there is an ideal solution for this problem. The solution was described by Brad Victor in his The Future of Programming presentation. The best API is not to have the API at all. In other words, the best communication protocol is when two computers figure out how to talk with each other. And this idea is not that unique at all. There is a movie, Colossus: The Forbidden Project. The movie is from year 1970. In this movie, two supercomputers figure out how to talk with each other without the help of a man. But let's get back to the REST API. Let's try to understand the reasons of disagreement between two engineers. First, the native mobile app engineer who doesn't want to query an additional endpoint. The developer is afraid of increased loading time because that directly affects user experience in the app. The developer is also afraid of the congestion of device networking stack. Multiple requests require some synchronization code. That will probably cause a code duplication on each front-end platform. The developer is also afraid of getting too much of unneeded data. And finally, the mobile developer also thinks about increased battery consumption. Well, these points are all serious issues, but are they everything? Are they the whole picture? What about the microservice developer? Microservice developer sees other perspective. He or she doesn't want to contaminate the hotel service domain with the hotel reviews service domain. This would make the hotel service, much harder to maintain. Next, domain contamination will cause data ownership issues. Should the hotel service be responsible for the data? Should the hotel service just transfer the reviews data by? Next, backend developer is afraid of giving too many promises. Adding just anything to the API endpoint to the API response means it will basically stay there forever. Because removing the data in the future would break some clients, so existing clients or like older app versions. Also, more responsibilities means more opportunities to fail. The performance of hotel service would be bound to the performance of reviews service. Now let's try to think, how can we fix this issue without neither extending the app nor extending the hotel service. So, the second part of my presentation. Let's talk about different HTTP versions. Some of you have just finished their summer vacation. Imagine you went for a vacation to Croatia on the south of Europe, and you have a family in Poland, Central Europe. Imagine you agreed to share photos from your vacation. Unfortunately, the internet connection is currently unavailable, but you are free to send as many postcards as you like. Let's assume they are cheap. Actually, in the absence of the internet, you agree with your family you are going to use postcards as IP packets. Postcards will be addressed with either your home address or a hotel address, just like an IP address in IP packets. Postcards are a rather unreliable way of transferring anything. That's why you need to implement TCP on top of your postcards-based physical link. You would like for your correspondence to remain private. Your grandma suggests TLS. You agree, that's a good idea. And that's not all. Your family would like to directly specify what pictures exactly do they want to see. That's why you all decide to use HTTP. Thanks to HTTP, you will also have an option to just reply HTTP forbidden on your discretion. So let's see if that really works. Let's imagine that a single postcard travels from Croatia through the postal routers in Zagreb, Budapest, Bratislava, Prague, and Warsaw. And imagine it takes just one day to deliver a single postcard end-to-end, no matter the direction. Let's see how long will it take to transfer one single photo. Let's connect with my avatar in Croatia. He can hear us, but he can't speak. He will play the main character in this story. He will help us to understand what's going on. On the top right, you can see a calendar. So it's day one. And how does the connection look like? So on the first day, his family sends him a postcard with TCP synchronize command. And he gets this postcard on the day number 2. He sends back TCP synchronize and acknowledge postcard. They receive it on the day number 3. The family sends him the final TCP acknowledge message. And to save time a little bit, his family already proceeds with TLS, so they send him a client hello postcard with their random number. He gets both postcards on the day number 4. The very same day, he sends them back a server hello with his SSL certificate and his random number. On the day number 5, his family validates his certificate. They send him an encrypted pre-master secret. He receives the encrypted message on the day number 6. Only he can decrypt the pre-master secret because family used his public key for encryption. Now my avatar can calculate an SSL session key using his random number, his family random number, and the pre-master secret. His family already knew the SSL session key the day before because they had all the data for this calculation. In the end of handshake, he sends home an SSL finished postcard to make sure his secure connection works. On the day number 7, his family receives the final handshake postcard. They can finally ask for the image they are interested in. That was tough, but now it will be a bit faster. His family wants to ask him for an image. So on the day number 7, they send him a postcard with session key encrypted HTTP request. On the day number 8, he receives the encrypted postcard saying, "Get first photo." 7 days passed, and he knows that his family asks for the first vacation photo. The photo is big, so he first splits it to chunks, so each of these chunks could fit the postcard. Then he encrypts each chunk with the negotiated SSL session key. He ends up with 1,000 postcards. He starts sending them one by one. The post office near the hotel is small. They can only take 100 postcards each day, but they do their best and take as many as they can. On the day number 9, his family starts receiving his postcards, one by one, about 100 postcards a day. His family sends him a first acknowledgement. On the day number 10, he receives an acknowledged postcard saying, "Good work, kid, we have already received 90 cards." He doesn't stop sending them. The next day, he receives a postcard with acknowledgement that they received 190 cards. On the day number 12, he gets the postcards asking for a transmission of the postcard number 342, as this postcard seems to be missing, seems to be lost somewhere along the road. So he sends the copy of this lost postcard and continues to send other postcards as well. On the day number 19, his family gets the final postcard and sends him a final TCP acknowledge to let him know that they already have the whole photo, all the packets. But it would be unkind to finish the connection just like that, so they also send him a TCP finish postcard saying they miss him. On the day number 20, he receives the goodbye words. Now it's his time to say goodbye, so he sends them acknowledge finish, saying that he knows they miss him and he misses them too. On the day number 21, they receive his message, and they send him a finished postcard saying the connection is finally over. He receives this final card on the day number 22. So now the transfer is finished. Thank you for your help, my avatar. Have a great time in Croatia. Bye. Let's summarize this up. It took 21 days to send a single photo, about 11 days for sending the actual photo data, which includes 1000 cards, many acknowledgements, few retransmission requests, few actual retransmissions. Post office was really busy that time. What was happening during remaining 10 days? During the first 7 days and the last 3 days? Really not much. There was a lot of blocking and waiting. And this was HTTP 1.0. Just imagine your family wants to get more photos. It's very likely they will. After each such TCP SSL connection, after each request, connection is being closed and open again for a new request with all the handshakes and then closed again. That's why HTTP 1.1 was introduced, because clients used to request more than one resource. Let's see this HTTP version on the diagram. In HTTP 1.1, your family and you don't close the TCP connection. You don't close the SSL session, but instead you keep the connection ready to get another HTTP request from your family. But imagine your whole family wants to get different images at once, simultaneously. What should they do? Well, they can take an example from web browsers. Web browsers usually start few TCP connections per host for HTTP 1.1. Each family member can create a connection for the same hotel in Croatia. Multiple connections doesn't mean the transfer is faster. You still have the same processing capacity. Everyone will need to wait for photos longer. We rather don't see any HTTP older than version 1.1 in the modern internet. I created a sample mobile app to demonstrate you how does it feel to use HTTP 1.1 to fetch a lot of resources at once. I will open the photo gallery. The photos are being fetched with HTTP 1.1 protocol. The app requests all the photos at once. As you can see, actual photos from my vacation are downloaded sequentially, and few appear at similar time. That's because networking stack on iOS by default opens 6 HTTP 1.1 connections per host. So there are 6 sequential pipes for vacation images. So when there are a lot of resources to be downloaded, those pipes get blocked. Can we do something about it? Yes, there is an HTTP 2. Let's try to update this Polish-Croatian connection to HTTP 2. First major difference. HTTP 2 handles multiple requests simultaneously in one connection. So your whole family sets up the TCP connection and SSL session just once. Your family can request new photos anytime, even during the active transmission of few other photos. Second difference. You and your family can negotiate on the priority of different photos. Third major difference. When someone asks a photo for the beach, you as a server can think, this time at the beach was really awesome. They will love all the other pictures, and you can send some additional photos before they even request for those. In the real life, this feature is used to push CSS and script files when the web page is requested. This feature greatly reduces the round-trip time and initial page loading time. As you have seen in HTTP 1.0 example, the transmission can get slow because additional round trips increase awaiting time. Number of round trips is now greatly reduced. I would like to show you the sample mobile app one more time, this time to demonstrate you how does it feel to use HTTP2 to fetch a lot of resources at once. I will open the photo gallery, and the photos are being fetched with HTTP2 protocol. The app requests all the photos at once. As you can see, photos from my vacation are downloaded in really random order without any obvious sequencing. That's a default configuration. Does it make HTTP2 faster than HTTP 1.1? Well, this was very naive use case. I'm downloading large files here. One such file takes few megabytes. There are millions of IP packets with photos, data, and very few round trips. So any way we organize this data doesn't make the network faster. But to give you a different example of what does it mean to be faster, let's imagine that all HTTP 1.1 connections are currently blocked by requests for large photos, and there are a lot of photos waiting in the queue. Then imagine some very small request that is initiated by the user tapping, for example, favorite star button on one of these photos. The request will wait in the queue until all the photos are downloaded. The user knows that downloading all the photos will be slow, but the user doesn't understand why does it take so long to finish one small user-initiated action. In case of HTTP2, such a small action can be prioritized and pushed to the server ahead of time, making the user feel the app is much faster. Is HTTP2 perfect? Well, almost. It has one design flaw, which is the TCP itself. I already mentioned my avatar doing TCP retransmissions in Croatia. Imagine downloading a lot of photos simultaneously, getting a lot of IP packets, each packet carrying TCP frame, each TCP frame carrying HTTP2 chunk. Your family gets a lot of postcards, and a single postcard carrying information about one particular photo is lost. You will have to retransmit the single postcard, which of course affects downloading the single particular photo, this yellow photo from yellow chunk, but because HTTP uses one TCP stream, download process for all the photos is affected. All other received postcards need to wait in order until retransmitted packet comes again. So lost postcards have a big impact on the whole TCP communication. And HTTP2 used to be the latest version of HTTP protocol. In June 2022, an RFC for HTTP 3 was published. The RFC has only 3 months, and Cloudflare reports that HTTP 3 is already over 30% of the internet traffic. Wow! Google has been using Chrome browser from few years as a production sandbox for draft versions of HTTP 3. HTTP 3 full name is HTTP through QUIC. QUIC is a replacement for TCP and is built on top of UDP. QUIC allows multiplex data streams over one UDP channel. In HTTP2, when one TCP packet was lost, all later packets waited until the lost packet is retransmitted. In QUIC, the lost packet only affects the single data stream. All other streams are unaffected. As you can see in the diagram, just a yellow data stream has been blocked because of lost packets. But the green and the blue data stream, they are continuing to be received. So this multiplexing feature introduced in HTTP2 was moved down in the networking stack to the QUIC protocol. I mentioned QUIC being a replacement for TCP. TCP is a very old protocol, but it had some improvements in recent years. For example, TCP multipath standard. TCP multipath allows the TCP connection to be transmitted faster, utilizing multiple network interfaces at once. QUIC addresses similar use case. QUIC connection migration will make a big change for mobile applications. Imagine using your home Wi-Fi network to start a file download. 1 packet, 2 packets, and then you leave your flat only to realize that the download stopped because you lost the Wi-Fi connection. With QUIC, this will no longer be the case, as every QUIC connection is identified by its connection ID. If you lose Wi-Fi connection, your QUIC compatible client will try to use different interface, in this example a cellular network. I tried to check the connection migration using my phone. I started downloading some large file with HTTP3 protocol and went for a walk. As soon as I lost my home Wi-Fi connection in the lift, the download unfortunately stopped. So it seems that not all parts of the QUIC protocol are implemented yet. Good news is that QUIC is a user space protocol. It took very long time for TCP multipath to be merged into Linux kernel. As you can see in this tweet, this was quite an event. In contrast, Google was releasing implementations for each new QUIC protocol draft using Google Chrome updates. No operating system kernel updates needed. Kernel knows only about the UDP protocol, and that's enough for all the operating systems. QUIC also allows to speed up the whole handshake process. I tried to measure call to request time for a very small 10 bytes payload for all the HTTP versions. The HTTP over TCP was 2 times slower when compared to HTTP over QUIC. I also measured the request time for a cellular network. This time, QUIC call to requests was also 2 times faster. Then I tried measuring the round trip for 3G network. This time, QUIC was more than 2 times faster from TCP. In the end, I just measured the request when using the really slow edge network. This time, the QUIC connection was about 3 times faster. Latest HTTP versions provide great improvements. HTTP 2 and HTTP 3 protocols support concurrent streams with prioritization. HTTP 3 additionally improves connection durability and reduces network lag. On the one hand, latest HTTP versions encourage to run multiple requests at once, but on the other hand, there are other problems with many connections. Let's jump into the next topic. We'll talk about the response payload size. Quick to the business. Take a look at loading times for a few different payload sizes. First, when using Wi-Fi 6, 10 bytes, 100 kilobytes, 200 kilobytes, and the last bar, 300 kilobytes. All those bars seem to be very similar. Now let's add measurements for slower network, for LTE network. Well, this doesn't look good anymore. It starts to grow really fast. I also measured request times for 3G network. As you can see, the slower the network, the bigger the impact of the payload size on the loading time. When requesting for remote data, it is particularly important for the mobile apps to only fetch the data that is actually used in the app. There is a standard approach for limiting the payload size and aggregating multiple requests, and this is BFF. BFF is an acronym for backend for frontend. Having in mind all the stuff about network lag I have told you about, BFF at first seems like a very bad idea for the network latency. In a moment, you will see it is not true that it's a really good idea. But let's try to think why it may seem like a bad idea. Imagine a mobile client, a BFF service, and the service A. Mobile client's request for BFF for the data. BFF asks the service A for the data, and BFF receives the data from the service A. In that step, BFF waits for all the packets of the response. The whole IP packet train needs to stop at BFF station before the next IP packets train could leave the BFF heading to mobile client. Only after the BFF receives the last packet of the answer from service A, the BFF can start transferring the response to the client. So regarding receiving the first byte of the response, yes, BFF makes it slower, but when dealing with JSONs, we are rather interested with the last byte of the response. So we need to measure the whole transmission. I created a sandbox for an experiment. 3 services there. a service A, which is a sample domain service, good BFF, which is a sample GraphQL-based BFF that always returns a small 1 kilobyte payload, and bad BFF, which is a sample GraphQL-based BFF as well, but this BFF returns the payload from service A without any change. It returns the payload as it is. Those services were running on different instances of virtual machines in the same data center in Germany. I measured average response times from all those services. In the case of small payload from the domain service, we can see almost no time difference between asking both BFFs and asking the domain service. But when we start making the domain service payload bigger, we can see increased response access time when not using a good BFF. As you can see, bad BFF is even worse from directly calling the service A. So, as expected. And this graph only shows the measurements for the Wi-Fi connection. Let's see the measurements for 3G connection. As you can see, small differences in network payload size result in the response being much slower when not using good BFF, especially when using a slow network interface. When using good BFF, clients will not be affected by additional unused data in a domain service. These are measurements for a toy project. If you don't have a companion BFF for your app, I encourage you to choose one sample response that your app uses, and I encourage you to strip this response from all unused data and compare the size with the original. The last part of my presentation, let's summarize this all. What about the answer to the question, the ultimate question, one or many HTTP requests? First, ask yourself, what is your target? The good answer could be, I think the good answer could be flawless user experience. UI should be as fast as possible, as fast and responsive, even on a slow internet connection. How to achieve this target? First, consider migrating to HTTP 2. Consider also supporting HTTP 3. Secondly, consider using BFF to limit the payload size and to aggregate upstream requests. Finally, BFF is not a silver bullet. Consider using multiple requests to lazy load the screen content. Always talk about alternatives with your user experience designer. Also, try to measure stuff. Try to measure your response requests. And that is an end of my presentation. Now, unfortunately, I have to turn the dark mode off. Please put on your glasses or close your eyes. And thank you.